Hi, I'm Sean Gannon, and this is Minute Math, and today we're learning about evaluating limits.
Minute Math, when you need help you use Minute Math.
We're given this problem right here. The limit as x approaches 1 from the right, the plus sign there, of 4x plus 4 over the absolute value of x plus 1. Now we have that graph right here given to us. But what do we have to interpret with this problem? Now, this is the graph of 4x plus 4 over the absolute value of x plus 1. And the limit says we have to approach, what happens when we approach 1, but it specifically tells us the plus sign from the right. So we look at our graph and we approach, when x is 1, we have to see what is that y value there. So when x is 1, the y value, as we approach 1 from the right, notice that the y value is all 4, right, until it hits 1 and it doesn't equal 1, right? X can't be 1 here, but it doesn't matter. We're approaching from the right. So we see at the top there that when x approaches 1 from the right, we hit a positive 4, okay? And so here, this limit, right, is going to be equal to a positive 4, and that's where it's approaching from the right. We're given this problem right here. The limit as x approaches a negative 1 from the left of f of x. And f of x is equal to the piecewise function negative x minus 8, where x is less than or equal to negative 1, and negative x squared minus 4x minus 4 when x is greater than a negative 1. And we can see that in our graph here that's provided. Now notice here, they said we have to find when x is approaching a negative 1. And notice that's where the jump happens. So we really have to interpret where in this graph we're going for, which line. And that comes right here, with the negative up top as almost like an exponent. That means we're approaching negative 1 from the left. So we look at our graph there, and we're approaching from the left, right? And we see the equation that's going downwards, right? So we're approaching negative 1 from the left, and the equation sloping downwards, and it actually hits that point right there. Okay, we see the point goes down, and so when x is negative 1 there, it's approaching negative 1 from the left. It's approaching a y value of negative 7. Okay, so we see that it's approaching down there to the negative 7, and so our limit here, right, I'm going to rewrite this, I guess, limit as x approaches a negative 1 from the left of f of x is equal to a negative 7, right there. We're given this limit right here, the limit as x approaches a negative 3 of f of x, where f of x is equal to the piecewise function negative x squared minus 10x minus 24 when x is less than or equal to negative 3, and 2x plus 3 when x is greater than a negative 3. All right? And we need to evaluate this limit. So they tell us here we're finding when x approaches a negative 3. We can see on the graph that at negative 3, both of these functions here actually match. They meet up right there at negative 3. And it's important to note that here because when we just have the limit as x approaches negative 3, it has to approach both the left and right hand side together. Well, they've both reached the same point there, the y value at negative 3. They're both approaching, when x is negative 3, to the y value of actually a negative 3 right there. So we would say that this limit as x approaches a negative 3 of f of x is equal to a negative 3. And that is our final answer. We're given this problem right here, the limit as x approaches a negative 1 of f of x, where f of x is equal to the piecewise function of x when x is less than a negative 1, and negative x squared plus 2x when x is greater than or equal to a negative 1, and we can see the graph here. Well, we need to find this limit at x equals negative 1. So we have to see both sides from the left and the right where it comes together there. Okay, so where are they approaching? Well, our first equation from the left, we're going to be using y equals x here, or f of x, right, equals x. And we see it's approaching the graph there, and it's approaching from the left there to negative 1. There's an open circle there, but again, we're approaching when x is negative 1, the y value is negative 1. But from the right, we use the second equation, negative x squared plus 2x, and we're approaching from the right here, and that actually approaches when x is negative 1. Our y value is a negative 3 here. And so what happens is we have from the left and right, while we're approaching, when x is negative 1, approaching negative 1, they're approaching two different values. So what happens? What do we do there? Well, when that happens, we would say that the limit of x approaches -1 of f of x isn't really approaching any specific value, right? There's two different ones there. So we would say this is a DNE, which stands for does not exist. Capitalized, whatever. And there we go. So our final answer here is that this limit does not exist. We're given this problem right here. The limit of x as it approaches -1 from the left of f of x, where f of x is equal to the piecewise function -x minus 3, where x is less than or equal to -1, and then x plus 1, where x is greater than -1, and we need to evaluate this limit. Now this is kind of tricky here, and then we can sketch this graph, okay? So if we want to graph just f of x here, we can see that right here. Now, that graph shows the piecewise function. We have the -x minus 3 for when x is less than or equal to -1, and then the x plus 1 where x is greater than -1. And graphing this actually helps us really find this limit. We have to approach where x approaches a -1 from the left, because you see the jump is happening here when x is -1. And when we approach from the left, we're using the top equation right here. And where is it approaching? So we approach when x gets closer and closer to -1 from the left-hand side, our y value approaches, can you guess it or see it? -2. So in -2, we see that's the y value there. So we would say that our limit here as x approaches a -1 from the left of f of x is equal to a -2. We're given this problem right here. The limit as x approaches -2 of f of x. Now f of x is a piecewise function where -x squared minus 4x minus 5 occurs when x is less than or equal to -2, and f of x equals a -1 when x is greater than a -2. Okay. Well, when we evaluate this limit, we can graph it, and we can see the graph right here. Notice that these two graphs actually intersect, right, or touch each other basically, almost. Not technically because of this stuff, but right there when x is equal to a -2, which kind of helps us here, and that's what we wanted, okay? Because when we approach x to be a -2 here, when we look at that, we have to look at the left and right-hand side. Now, luckily for us, when they approach from the left and right-hand side, right, they approach the same exact y value, and that's what we're looking for. We're not finding when x is equal to -2, what happens when we approach -2 from both sides. And that y value is a -1. So we would say that our limit here, as x approaches a -2 of f of x, is equal to the y value of -1. And that is our final answer. We're given this problem right here. The limit of x, or as x approaches 0 from the right of f of x, where f of x is equal to the piecewise function of 1 when x is less than or equal to 0, and -x squared plus 4x minus 3 when x is greater than 0. All right. Now, one thing we want to note here with this limit, we're not really given a graph or anything like that. We're going to do it without it. We want to see when x approaches 0 from the right. So if we're coming from the right, all the values leading up to it will be positive or greater than 0. Okay? So we're going to focus on this second equation right here. Now, what do we know about the second equation? If we ignore the value here of x is greater than 0, it's a continuous function, right? It continues left and right. The domain is all real numbers without this restricted domain. So if we're approaching from the right, and we know it's essentially, right, unrestricted domain, we actually can just plug in that value because it's continuous, right? So we can plug in when x is 0 here to find what this limit's going to be. So we take the negative, put a 0 in for x squared, plus 4 times 0 minus 3, and let's simplify this, right? Or solve it, right? When f of 0, we'll solve it. Well, 0 squared 0, don't need anything there. 4 times 0 is 0, and we have minus 3. Well, minus 3 is just left over. So what that tells us here that the limit as x approaches 0 from the right of f of x is equal to a -3. And that is our final answer. We're given this limit right here. The limit as x approaches 0 from the left of the absolute value of x over x, and we need to evaluate this limit. Now this one's a little tricky, and I'm going to use a table here to try to see what's going on, what's happening at 0, right? Because really, we can't plug 0 into this equation. So if we use a table of just, x and f of x, let's see what happens when we plug in as we approach 0 from both sides, and then we'll go from there. If I put a negative 3 in for x, what happens? Well, the numerator here, negative 3 goes in, becomes a positive 3, right, with the absolute value, but we're divided by negative 3. So the overall equation becomes a negative 1. If we plug negative 2 in, same thing. Negative 2 in for x, absolute value makes a positive 2, dividing it by negative 2, negative 1. We do the same thing with negative 1. Up top becomes a positive 1, divided by negative 1, negative 1. 0 we can't really put in there. It does not exist. Right? We can't divide it by 0. But if we put a positive 1 in, absolute value of positive 1 is 1, divided by itself, 1. Put a 2 in, same idea. Absolute value of 2 is 2, divided by 2 is 1. And lastly, cube of 3, absolute value of 3 is 3, divided by 3 itself is 3. Oh, is 1. I almost went through it. I was wondering if I was going to make that mistake. We have a 1 there. I can't believe I did that. All right. So what happens here? Well, when x is negative, our output is just a negative 1. When x is a positive 1, or positive, our output's a positive 1. So we're approaching 0, right? That does not exist, and we're approaching from the left there. So if we're approaching from the left, it's going to approach, well, the negative values is always going to be negative leading up to 0. That means we're approaching the y value of a negative 1. And so this limit here is equal to negative 1, and that's our final answer. We're given this limit right here, and it's a tricky one. The limit as x approaches 0 from the right of the floor of negative 2x plus 1. And the floor, so the floor you'll see is that symbol. We take the floor of x is really the greatest integer less than or equal to x. And we'd see it as like the floor of x. That's how you pronounce it. So what does that actually mean? Okay, so let's go test what happens when x approaches 0 from the right. Okay, we're approaching from the right here. Okay, approaching 0 from the right, well, we can see we use a little table here. Okay, so if we put x and y here, or f of x, doesn't matter. We're approaching 0 from the right. We can't just plug in 0 directly to get an answer. We're going to see what it's approaching here. Okay, so if we have a, let's go with a, was it a 1/2? Let's go 1/2 here. 1/2 in for x. What happens? 1/2 in for x, right? A negative 2 times a 1/2 comes out to be negative 1, plus 1 is a 0, right? So we approach a 0. So we have negative 1/2, negative 1 plus 1 is a 0 there. All right, so it actually hit the integer right off the bat here. Well, what happens, let's go a little smaller, a 1/4 here. So let's do some work here. If we have a 1/4, so negative 2 times a 1/4 plus 1. Negative 2 times a 1/4 is a negative 1/2, and then we add 1 to that. Negative 1/2 plus 1 here, right, is a negative 1/2. That's our positive 1/2. Positive 1/2, I got thrown off here. All right, but I'm not going to plug just 1/2 in there. We're taking the floor of that output, the greatest integer less than or equal to that 1/2, which is 0. Let's do another one here. Let's go 1/10th, let's say. So we put a 1/10 in as we get closer and closer to 0 from the right. So negative 2 times a 1/10 plus 1. Negative 2 times a 1/10 is a negative, well, that's a 1/5 plus 1. And negative 1/5 plus 1 comes out to be, well, negative 5th plus 1 is a 4/5. That's still less than 1 here. So the greatest integer less than or equal to 4/5 is 0. Okay? Now what happens if we actually plug in 0 for x? Negative 2 times 0 plus 1. Negative 2 times 0 is 0 plus 1 is 1. But this is the key here when we say we approach 0 from the right. We're not actually plugging in 0, right? So 0 in is a 1, but that's not going to be our limit here. Okay, again, we're approaching from the right, not actually plugging it in, and that's where the jump happens. So if we're approaching from the right here, right, 0 from the right, it's approaching a value, a y value of 0 when we use the floor function. So this limit here, or I'll rewrite it, as x approaches 0 from the right, the floor of negative 2x plus 1 is equal to 0. That one's tricky, but it's our final answer. We're given this problem right here, the limit as x approaches 1 of f of x. f of x is our piecewise function of x over 2 plus 9 over 2, where x is less than 1, and x squared minus 6x plus 10 when x is greater than or equal to 1. And we have to evaluate this limit. Now what's tricky is here, we can't just go plug in x equals 1 right off the bat. Well, in a second. We have to analyze our function here. If we ignore our restriction on the domain, both of these are continuous functions. We can plug any value in for x that we would like. Okay, we're good there. And we know that these functions will be continuous for both of them. So with that being said, we know we have to evaluate one from the left and right hand side. If we evaluate it from the left, we have the top function. And if we evaluate it from the right, we have the bottom function. And we can see that from our domain. So what I'm going to do now is I'm going to actually plug in when x is 1 for both of these functions. If they both equal that same value, then we can say our limit equals that. If they have different values that they equal to, that means they're approaching two different values, so our limit won't exist. So let's go do that. So for the first one here, let's plug in 1 in for x. We have 1 over 2 plus 9 over 2, right there. Well, 1 over 2 is a 1/2 plus a 9/2. 1/2 plus 9/2 is a 10/2. And 10 divided by 2 is 5. Okay? So from the left, our limit, if we approach 1 from the left, we approach a 5. But what about from the right? So let's go to the second equation. Again, we're going to put 1/2 in for x. 1/2 squared minus 6 times 1/2 plus 10. Well, 1/2 squared, or sorry, not 1/2, 1 squared. This is what I get for, see, I was thinking about the 1/2, but really it's a 1. See, that would make a mistake right there, so don't do that. All right, but good thing we caught it, and hey, we all make mistakes. Plug a 1 in for x, minus 6 times 1 plus 10, and this is a much easier problem now. 1 squared is 1, 6 times 1 is 6, and plus 10. 1 minus 6 is a negative 5, plus 10, and negative 5 plus 10 is a positive 5. So from the right and the left here, we both approach a 5. So that means that our limit here, as x approaches 1 of f of x, is equal to 5, and that is our final answer. We're given this problem right here. The limit, as x approaches negative 1, of 3 absolute value of x plus 1 over an x plus 1, and we need to evaluate this limit. To get a picture of this, I'm going to use a table here. Let's see what happens as we'll get close to negative 1. I know I can't put negative 1 in right away. It doesn't exist because we're really dividing by 0 there. So we do a table. We have our x and our y here. If we put a negative 3 in for x, let's say, negative 3 here in the top part, we have negative 3 plus 1 is a negative 2. Absolute value of that makes it a positive 2, right? Well, then we multiply by 3, we get a 6. The denominator, we have a negative 3 plus 1, which is a negative 2, and 6 divided by a negative 2 is a negative 3. Okay? Interesting. Well, what happens if we put a negative 2 in? All right, let's keep going down. Negative 2 in for x. Negative 2 plus 1 is a negative 1. Make that positive with the absolute value, and we have a 3 up top. And then we have a negative 2 plus 1 is a negative 1. So 3 divided by negative 1 is a negative 3. Again, we have it there. If we plug a negative 1 in here for x, well, it doesn't exist, right? We can't put negative 1 in the denominator. It gets us a 0 there. DNE. But a positive 1, we put that in. What happens when we have a positive 1? Well, 1 plus 1 is a 2, and a 2 times a 3 is a 6. 1 in for x down here, 1 plus 1 is a 2, and then 6 divided by 2 is a positive 3. So what's actually happening with this function here? Well, what this actually looks like, if we make a quick sketch of this, this function is basically doing this. And this happens sometimes when you have your absolute values of the same thing over itself. Our function here, all right, looks something like this. And this is at a negative 1. and this is a -3, and this is a +3 up here for the y value. Okay? So our function here is doing something where if we approach from the left, it's always going to be a -3, and then it hits, there's nothing there at -1, and then it jumps, and then -1 greater than -1, it's a +3. Okay? Oh, I guess I could have shown 0 here to make it a little easier here for you. 0 and for 0 here, 1, and then 3 up top, right? And then divided by 1 is 3. Skip that one. Sorry. Well, with that, we can see then from the -1 here, it has two different values that's approaching from the left and the right. So when that happens, when we approach different values from the left and the right of -1 here, we would say that this limit does not exist. And that is our final answer. We're given this problem right here. The limit as x approaches -2 of f of x, where f of x is equal to the piecewise function x squared, where x is less than or equal to -2, and -x/2 plus 3 when x is greater than -2. And we have to evaluate this limit. Well, what we want to look at is both of these functions here. Ignore the restriction on the domain here. Both of these functions are continuous. Okay, and then specifically they're continuous at -2. Okay, so that allows us here to evaluate this limit by just plugging a -2 in for both of these x values, and we can see that whatever the output is where they're approaching from the respective left and right here. So let's deal with the top part here, the first one. What happens when we plug a -2 in for x? We have -2 squared. That's easy. -2 squared is, well, +4. Right? So now the second equation will see the same thing. -2 in for x. So we have a -2 in for x over 2, negative out front, plus 3. Negative and negative make it a positive, so we have +2 over 2, plus 3. And 2 over 2 is 1, plus 3. And 1 plus 3 is 4. So from the, this is the left, and this is from the right, at -2, we are both approaching 4. They're both the same value on left and right where it's approaching, so we can say that the limit here, as x approaches the -2 of f of x, is equal to a +4, and that is our final answer. We're given this critical thinking question. Give an example of a two-sided limit of a piecewise function where the limit does not exist. So we have to do a piecewise function, and we find the limit doesn't exist. And generally, a good goal here is you want the left and right hand side to approach two different values. Okay? So there's many actually answers here that can be. We'll have one here. So it's right here the limit. Let's say when x is equal to or approaches 1 here of our function f of x. And this function here, f of x, we have to make it a piecewise function. Okay, we'll have two parts. Let's say our function here is equal to 0 when x is less than 1, the 1 value here. So when x is less than 1, our whole function is just equal to 0. Let's make a jump here. Okay, let's say our function is equal to, well, let's make it equal to 1 when x is greater than or equal to 1. So we notice here, when for all values x is greater than or equal to a +1, we jump to be a +1 here as the y value. So we can see this graph here, if we did a quick little graph of it. All right, we have the x and the y. We have this function at 1 right here. With all the x values less than 1, it's equal to 0. So our graph is right on the x-axis here, and we have an open circle right there. We have a height of 1 when x is 1 or larger. So we have a closed circle there, it's equal to, and it goes to the right. And we can see now at x equals 1, right, or as x approaches 1 from the left and right, it's two different values, so our limit does not exist. And there we have an example for you. We're given this critical thinking question. Give an example of a two-sided limit of a function with an absolute value where the limit does not exist. Well, there's many answers actually for this one here, but we have to deal with an absolute value here, but like I said, many options. Let's keep it simple, start building this. Let's say limit as x approaches 0. Okay, so if x approaches 0, we can say we have the absolute value of x here. Let's do that, and then over itself. Okay, so we know that any number we plug in besides 0, when we divide it by itself, it's always going to be equal to 1, right? 0 doesn't exist right here at 0 because, well, we can't divide by 0, but that's not why this limit would not exist there. Let's use a table here to see what's going on. We have our x and y value. If I put a -2 in, let's say, -2 in for x, and so the absolute value becomes a +2. We divide that by a -2, and so we get a -1. Do the same thing with -1 here, and for x, +1, divided by -1, -1. 0 does not exist at 0, right? What about a +1? What happens here? 1 in the absolute value of 1 divided by 1, +1. Do the same thing with 2, and we get a positive, I almost did it again, it's a +1 right there. So on either side, as x approaches 0, when it's from the left, we approach a -1. When it's from the right, we approach a +1. And so that happens, it's disjointed there, it doesn't connect, right? Not continuous. And so at 0, the limit doesn't exist there because the left and right would be different. So here is an example of that, but you really could do a lot with absolute values divided by itself here, not specific values. So anyway, the limit here does not exist, and that's our final answer. I hope this video was helpful for you, and if it was, please subscribe to this YouTube channel and like this video. This helps us make more free math lessons for you and for everyone else. So as always, thanks for watching.
Minute Math, when you need help you use Minute Math.